Hello there. My name is Mark Wardle. I'm a neurologist really, but I also do software development and built a lot of open source tools that I use in clinical and research applications. This is just a live coding demonstration really to show how I approach building different bits of software and functionality. The main repositories here are on GitHub/Wardle. The biggest application is Hermes, which is a SNOMED CT terminology server. So this gives capabilities to your application, whether you're running as a microservice, a kind of HTTP server, or embedding it in as a library into a bigger application. So Hermes basically provides a wrapper around SNOMED CT, and you can use all of the data within SNOMED CT and do all the inferences that you would expect from a clinical ontology. So, simple questions like, does this patient have multiple sclerosis or a type of motor neurone disease, or is this patient on a calcium channel blocker type drug, or that kind of question. And you just want to make that kind of functionality really easy to use in other applications. So this is a module essentially in a larger suite of services. And PC4 is Patient Care 4, which is the fourth iteration of my patient care electronic record system, which is used in clinical research and also in day-to-day clinical use in a number of departments within NHS Wales. There are other repositories here giving similar functionality to different kinds of data. This is all really about data. So one of the issues that we've got is I would like to identify cohorts of patients that match different ICD-10 codes. So ICD-10 is a classification system. So for example, G35 corresponds to multiple sclerosis. So obviously we can manually turn those into SNOMED identifiers and then use the SNOMED CT expression constraint language. So we could do that, and let's do that to start with, just to see it as a demonstration. So this is so I've got multiple screens set up here, and I try to avoid lots of distractions when I'm doing coding. So this is the Hermes application. And let's close that for a second. And so Hermes is a closure application and library. And closure is a Lisp, and it's a very concise language, and it's a very powerful language, and it really comes into its own when you're dealing with data. And it's a functional language, so rather than thinking about lots of state and changing things in place, you are better thinking about data flowing and being modified as it flows perhaps, and being validated and checked. But we're thinking about flows. And so mostly things are immutable, so that we don't change things. And most of the services that I've built are immutable. So once you've created a SNOMED CT terminology server, you just leave it alone. And if you need to have a new version, because they're released every quarter, then you just spin up a new service and switch at the API gateway layer, rather than trying to update in place. I find that much more powerful, much simpler, easier to implement, and less buggy. And of course, if there's a problem with the latest distribution that's outside of what we can control, I can just flip back to the previous version. I've not destroyed anything. I've not rebuilt indexes, because it's all new. It's the more modern approach, really. In the olden days, people used to run a server. They gave it a name, so you could think of it as a pet. Whereas nowadays, we're much more likely to think of data and computing services as cattle. You don't give your cattle on a farm each a name, and they're relatively substitutable. So it doesn't matter whether it's that cow or that cow. We're just bringing these services online and then discarding them if they fail, or discarding them if we don't need to use them, or keeping them around so that we've got some historic idea of what that service was returning at that time. That's very valuable in the medical sphere. The superpower of closure is the REPL. A REPL stands for read, evaluate, print and loop, and it means that I can basically type commands, really execute forms in the process of my running application. So my application is already running, so this is within Hermes here. So the first piece of work that we need to do is have a look at Hermes. And so we'll just have a look in the core. So this is the core API here, and this is a kind of standard closure type approach here. We're in this namespace, so it's a bit like a Java package. These are our dependencies for this code, and then you read the code top to bottom. So you know, this defines a service which encapsulates some Java stuff actually, which is a fast key value store, which is how this is all implemented. And we get higher and higher levels of abstraction down here. These bits down here are using the bits further up. And here you see a comment block, and comment blocks are really powerful, and I often leave them in the source code because it's a really good way of getting back to where I was when I was doing software development. So back to the REPL. So this REPL, I can type things. So Clojure uses prefix notation, so you put the verb first. So you start with parentheses, you put your verb, and then you put the parameters. And it supports variable length parameters, so this could be many different parameters, and then we can execute that. So we send that into the REPL, my program executes it, it's compiled and executed, and we get the answer 4. The interesting thing with prefix notation is that you don't have to worry or remember all of those precedents, the operator precedents that you have to in other languages. So for example, if I go 1 plus 2 and then we'll multiply 3 and 4, it's really obvious, I hope, that that will be executed first and then that will be executed. So let's find out what result we get. We get 15. So it's just explicit, but a very simple syntax actually. And of course we can write the verbs. So when we write a function, we're actually creating our own domain specific language. And so I always think of levels of abstraction. So Hermes abstracts away to SNOMED, the SNOMED terminology service completely under this handle called service. And all we need to do is give it a file name, and it opens that database and makes that available in my application. So let's do that now. Now, most of the time when I'm in a REPL, I don't type commands here. I actually type it in my IDE and then send the form over using a shortcut. So I'm using IntelliJ here, and I'm going to send this def, which defines service, to be open SNOMED CT. So open is defined as opening a read-only SNOMED service from the path. So here we've got our files, and here I've built a SNOMED distribution. It does that in about 10 minutes from the live latest release, and it uses my TRUD service to download and do that all automatically. So it's really easy. Where were we? Let's go back. And so here we are. So we're going to open a service, so we can send that form in. Oh, no, we can't. Go move into this namespace and load it first, of course. So once that's loaded and compiled this part of the application, it's done. So now we'll execute that, and we have a service. So we've got SNOMED CT, and I can't remember when this was created. Actually, it's created on the 18th of September, and here is some information. So we've got the drug extension and the clinical extension as well. So that's great. That's just what we want. So what can we do with this? Well, there are loads of different functions that I've built to wrap this service. So we can do a search here. So this is a search command, and I pass in data. So this is a hash map. This is what we're searching for. So imagine your user is typing in something and we want to auto-complete it, and then here's the constraint which constrains the search to bits and pieces of SNOMED CT. So this is a declarative way of defining that. So we might say give me all disorders, or give me all clinical features, or all diagnoses, or all drugs, or all this kind of stuff. So obviously here I've been testing whether So 2470007 actually is multiple sclerosis itself. So one would hope that you'd get multiple sclerosis. And of course, because I've used this parameter here, it will include all of the smaller, more granular subtypes of multiple sclerosis as well. But I guess if you wanted to do a search for all disorders, so that's the SNOMED CT concept identifier for clinical finding, we would hope that we'd get the same answer as well, and we do, of course, because we're looking for disorders. But say my user types in motor neuron disease, well, there we are, we get an answer. And we get it really quickly because this is all backed by Apache Lucene and this other key value store called MapDB. And mostly, if you've got enough memory, enough RAM on your server, then mostly that will all be satisfied without any disk I/O at all. It'll be brought into memory using a memory map file. So pretty quick, and it's optimized for speed, because when you're auto-completing, you need a response within 100 milliseconds at the most. I think we should be able to just get an idea. So if we just ask for that, so that's in 20 milliseconds. So that's going to have to pass that. There's a ton of complicated code here that passes SNOMED CT expressions and turns it into a Lucene expression essentially. So that's what that namespace does. That's all that namespace does. It's all modular. We can run and test that module totally in isolation with everything else. So that's quick. Obviously we can just get information about concepts. So if we just get a concept from our service, and we'll get 24770, then we get the standard SNOMED CT data that is kind of published by SNOMED International. I tend to find that's very useful. That doesn't actually tell you very much, and so I built a denormalized thing which pretty much gives you all of the information that you need about a specific concept. I don't think I've set up a nice. So we've got within that extended concept, we've got all that data about concept. We've got all the descriptions. We've got all the parent relationships. We've got the direct proximal relationships, and we've got any ref sets that concept is a member of. And actually, we can just drill into that. So if we go parent relationships, that a keyword is a function of a map. So when that data comes, we can actually then just get the parent relationship of that. So that's how you read that. I've done it wrong. So if we do that, so we get a map here. So this is the type, and then this is the transitive closure table for each of those relationships. So we can look at these in one of two ways. You can either, let's just switch over here, and if I switch to Chrome, we've got, so I've just used the SNOMED CT browser from NHS Digital. So if I type in that identifier here, we see that's an ISA. And so this is the slow way of doing it, and you can go and look this up, and that's fine. Finding site. But of course, what's interesting about this is that I'm actually in a REPL here, which means I can slice and dice this data as much as I want. So these are the keys. So I can just get the keys of that really easily, and so that's the keys. Well, then you say, well, okay, can I fetch the fully specified name for each of those? Well, we'll just map across those. So we'll create a little anonymous function here. Oh, sorry, on a different keyboard than normal, and we'll go get fully specified name service, and the percentage sign is just going to be the first parameter passed into this function. And there are more than one. There's more than one way of doing this, and there we are. So what are we going to get? So now we've looked up for each of those identifiers a description. Trouble is, I can't really read that. I've got a scroll, which is a real pain, and I'm very lazy. So in fact, I don't just want the fully specified name and all this structured data. I just want the term, which is just here. So what we need to do is map across and get the term as well. So if we just get the term of that, then we have pathological process, finding site, associated morphology, and is-a. And so that's the power of this, is that I really have got the whole of SNOMED CT at my fingertips, and it's really easy to process the data, flow it through, and do clever things with it. So so that's that. So I'm going to close that bit. Now, what the issue I've got, just to be clear about the problem statement, is that I want to be able to have an ICD-10 code like G35 and use the SNOMED CT mapping, cross maps. There's an extended cross map which will give me all the SNOMED identifiers, or for any SNOMED identifier, give me the ICD-10 code. So I can reverse that map. So if I've given an ICD-10 code, I want all the SNOMED identifiers. So actually, that kind of works already, but I'll show you what the problem is now. So I'm going to use a ReverseMap. So ReverseMap is an awfully simple function, which actually just calls an implementation function. So sometimes I do this quite commonly. This is a facade, this is my public API, and it's just delegating to the store, which is in the implementation. It means I can, if I change the implementation, I switch to a different backing store, none of this changes, it's all just abstractions. And that's really useful actually. I can keep this API the same, and it becomes additive, so if I add new functions, I just add it, and I try not to change old functions. Or I can deprecate them, of course, but I'll leave them there, and it will just get bigger. And that's not a problem. This is not a large amount of code. So store reverse map is in the weeds of the backing store, so it's a bit complicated, I suppose. But MapDB gives me access to persistent Java data structures, including maps and sets. So here I'm using a set, actually, a navigable set. So navigable set is a nice Java abstraction around a set. So a set has unique, so each member of a set is unique, of course, all the standard set expectations. So this is the map target component set within my backing store, and here I'm getting a subset. And the way I've built this is that it uses prefixes, so that say I want all of the reference set items in a ref set. Well, the way I've organised this is it begins with a long, 64-bit long representing the ref set ID. Then there's a variable length string, so the length will be prefixed at the beginning of that. But then you have a string which will be naturally ordered, so it'll be in order and sorted. That's important for later. And then you have two other longs, so two other 64-bit longs, which together make a UUID. So obviously a UUID is 128-bit, and so it's really easy to then convert. So what this does essentially is takes a subset, it looks for the string. This is the lower bound and this is the upper bound, so it's basically taking any items with that ref set and that string and returning all of the identifiers, and that turns it into a sequence, and then each one basically is a tuple of the ref set ID, the target, the string, so that might be G35, the item ID in two longs. I take that, ignore these two because we don't actually need these because we knew those before. So that's why I put an underscore there, just to kind of, otherwise my IDE will say it's not being used, which is kind of true, but that's for documentation purposes. So I remember what these are. And then I build a UUID, so the constructor here takes the most significant bits and the least significant bits, and that's exactly how it's built. So that basically turns a ref set ID and a arbitrary ICD-10 code, or some other code actually, it doesn't matter, it's a string, and turn it into a UUID. And then we have a separate function here which is called getRefSetItem, which basically takes a UUID and fetches the ref set. So that kind, and get ref set item just gets it from another bucket of the key value store, but this time it's a B tree map, so it's a very optimized. I think it's a heap or off heap. No, is it off heap? It's a backing store that's memory mapped, and so that will just get the data from the backing store, and the serialization happens automatically, and I haven't got time to talk about that today. So let's go back. How do I do that with this computer? Control Alt. So so that's get reverse map. So that's quite nice. So we can use that. So let's just try it out. We'll reverse map from ICD-10. Let's use G35 as that's an example I can think of. So we need the ICD-10 cross map ref set. So we're going to search our service for, so let's do ICD-10, and that should give us this. So we'll use that to start with, but we can talk about which one to use later, because that will come up. So we can search within the ICD-10 complex map reference set, and let's search for, let's see if it works, G35, and yes we do. So we've got a bunch of data here, quite difficult to see though, isn't it? So let's map across that. So we'll just map the referenced component and execute that. So suddenly we've got all the identifiers. Now, if we want to then map across that and get the fully specified names, we'll do exactly the same as we did before. So we'll get the term of the fully specified name of the service with the identifier of that, and then we will send that in, and that will give us ICD-10 mapped. So that's fantastic. So what work actually have we got to do? Well, I want to do something like this. So we need to take a code such as myasthenia gravis. So let's put ICD-10 myasthenia gravis. So we've got, let's use this one. So here we've got G70 and 0. Let's just check that that works. So we'll switch back here. Does it work? Oh my goodness, it does. So we've got all the myasthenic syndromes. Well, what if I just want all of the G70s? Oh, it doesn't work. And that's because we are doing exact matches. And that's a problem. That is the problem that we've got here. And the issue is we want to be able to do a prefix search. So that is our challenge for today, is to build a prefix search for ICD-10 or any other code system actually, because this is going to be generic. So we want, in any SNOMED cross map, take an arbitrary prefix and search and give me all the SNOMED identifiers for that, because many classification systems use a coding system where this is meaningful. So the G and the 7 and the 0 and the dot, and then a code means there's a kind of structure there. It's the classification. So you can see that here. So yeah, so we've got, I would like to include all of these. So I suppose there were two ways of looking at this. One is we could do the prefix search. The other option is to search the whole of all of the cross maps within that ref set. So that's all the congenital ones. That does work. So what we could do is get all the codes and then find the matches using regex. But I suspect that's going to be quite slow, because you're going to have to load up the whole ref set in one go, and then search on it using a regex. So the other option is that we use the characteristics of our backing store and the fact that we go from most significant to least significant in an array to do a prefix search like that, and I think that's what we'll do to start with at least. So let's do that. So let's go back and look at how ReverseMap works. So actually, I think what we're going to end up doing is coming into this store component here, this store namespace. So I think that we should start here. And so actually, we'll just take that code, and what we're going to do is go down to the bottom of this. And we're going to start at some stuff at the REPL. So we don't have our service here. That's in a different namespace. We're in the store now, so we're at a lower level of abstraction. I don't need to use the abstractions defined in that other namespace. Here we're going to be using a store instead. So here's a store, and this is a bit more low level. But pretty much mostly all of the other abstractions built in the other one are here. So pretty much it works as you'd expect. And in fact, because mostly the functions in the other one just simply delegate to here, most of the things are here. There's some minor differences, mainly due to language, because that's in a separate namespace, and ECL, so the SNOMED CT expression constraint language is in a different namespace, so that is kind of orthogonal to this bit, which is all about the store and the backing store. So this is all code that deals with the underlying implementation of that backing store. So what we have here is this subset business. So while we're messing about, we're going to we better use that ICD-10 identifier. What did we say it was? So we actually I can search in here as well, see whether we get the same response. Yes, we do. So that's the one we wanted. So let's use that, and we'll switch back. So I'm going to just stick that in there, and I'm going to stick that in there, and we're going to just see what we get when we use our G35 again. So this is kind of like just playing around. And I send that in, and so I'm writing essentially Java here. This gets converted into Java and is executed. Oh my goodness, what is this? So these are objects. Actually, these are arrays, and I can cheat. You can map across that. I don't want to do that. I want to map a sequence across that. So that's what's really behind the scenes there. This is just optimized. So here's the refset ID. Here's the ICD-10 code. Here are the 64 most significant bits, and here are the 64 least significant bits for each of the G35s. Fantastic. So what we really want when we type in a prefix, so what were we using for myasthenia gravis? So I want to put G70. So how are we going to do that? Well, so if I put G70, well, that's the wrong window. So G70.1 and G70.1. Perfect. So that works. Now, how are we going to do this? So the lovely thing with navigable set, if you have a look, is these. So given an element, we can find the least match and the greatest match, or because it's all ordered. That's the key of this, is we're dealing with ordered stuff, so we can use that to our advantage. So if we sorry, that's the wrong one again. So if we so this is how I call Java from Clojure. So we're calling ceiling on this. So let's just, for ease, we'll define our bucket. So we'll call it the map target component. We'll define that as that. So that just saves me typing loads. And we don't need that because that's just an optimization thing. So we can subset MTC, and then we'll get the ceiling. Let's just run that separately. So let's show you what we get. If we type in if we type in G70.1, we'll get the lowest entry, or that entry. So if I type in G70, suddenly we're winning, because now we've got a prefix search at least the lower bounds. So now that's kind of done. Our lower bounds is already done. So upper bounds is more complicated, because how are we going to do that? So we can use the floor, and we'll use the same. Well, that's not right at all. What we really want is to somehow put that in, and that will give us everything up to, but not including G71, which will give us anywhere between G70 and G70.9. We have our answer. So what we need to do actually is write something that will take an ICD-10 code and then just take the last digit and increase it a bit. And then we'll have a prefix search. Of course, the other option is that we allow our client to do that. And we could do that as well. That's not a bad idea. So first of all, let's think about how we're going to build something that will take a string and give a string that's a bit higher. And so what we can just build that here, and we'll make a function. And this is the joy of building enclosure, is that I get like really immediate feedback. So what I'm going to do first is define my string as, say, let's make it G70.1. No, we'll make it G70 for a good example. So we've got a string there, and I can send that in, and we get G70. Job done. How are we going to increase the character? Well, we can use the closure's core library for this. So we'll get the last digit, last character of our string, which is 0. We're going to turn it into an integer. God, this is going to be really easy. We can increment it. We get 49. And then I suppose we better turn that back into a char. So we'll turn it back into a character. So that's now 1. Is that right? Yes, that is right. And then we need to kind of join that with the rest of the string. So how are we going to get the rest of the string? Well, there's a function called but last, right? So but last will give me those characters, because what it does is it treats the string as an abstract collection of characters, which is great because it allows this string manipulation to work really easily. I'm not going to like accidentally use an index that's out of the string range, because this is all just dealing in the string as an abstraction of a sequential characters. So what you can do with a sequence of characters is use apply str to. So str is like a joining thing; it just makes it. So there we are, and then all we need to do is shove in our character here. So we'll apply str to the list of characters except the last one of our string, and then we'll take the last character of the string, turn it into an integer, increase it, and then turn it back into a character. So my goodness, that should work, but it doesn't. So don't know how to create a sequence from a character. That is kind of true. So yes, that is true. So what we need to do is, yeah, sorry, I've done that wrong, haven't I? Because that's already. So what we need to do is turn that into a string there, and then there. Yeah, so there we are. So sorry about that. So this takes the array of characters. That wasn't an array of characters, it was a single character. So we need to join. Strud just joins and turns everything into a string. So you just go bang, 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 and so it'll take, so that turns it into a string, that turns it into a string, that joins it all up. So that's quite good. So we can turn that into a function, look. So this is where it gets really easy. So we're going to define a function, and I guess we should call it something that's meaningful, that means it can stand alone. Because although we're only thinking of using this in this app, this little usage, we could call it something nonsense. It just helps when you come back to the code to remember what on earth it is. So I'm going to look for I'm going to call it prefix upper bound, because for a prefix search, we're going to define the upper bound of it. So we can say, well, given a string, generate an upper bound suitable for a prefix search. For example, 1, 2, 3 should give 1, 2, 4. We'll test that in a minute. So that's good. So in fact, actually, that's our function. So we can send that in. No, we can't. So sorry, it hasn't got the parameters. So we'll put in s there, and then. So basically, this says make a function. It takes a parameter string, and then it sends in here. So prefix upper bound, and we'll go G35. Sorry, I mistyped that. What's going on there? Prefix upper bound. Oh, I haven't moved into here. Sorry. G36. Perfect. And let's just test it with what we said. So 1, 2, 3. That's great. So it seems to work. Now, one of the things that's really nice when you're writing things like this is to think about testing. And so I quite like generative testing. So Clojure comes with that, so that we can send in a ton of made-up strings that are synthetically made, and you can really exercise your functions and check that your assumptions are correct. And it's often the case that your assumptions actually are not correct at all. Upper bound, and I think I've just spotted a problem that generative testing might help us with. So let's just prove it works in this new REPL. Yes, of course it does. So what you can do with generative testing is define a specification for the data that you want. We use Clojure spec for that. So I'm not going to import that properly. I'm just going to use that in the REPL here. So I will bring in Clojure spec alpha, and we'll bring that and alias it as S. So that brings in that library. And actually, I think we might need to do Clojure test check as well, just to bring in the generative testing. Check, and I think it's generator as gen. So why have I not got that working? Generators, sorry. Clojure test check. No, I may, sorry. Right, so this is, that's why. So I'm actually not using the right alias, so let's just start up again. So when I start my REPL within my IDE here, we can define the profiles that will be used. So the reason I couldn't pull out that library was that it wasn't in the dependencies. But what we should have now is we should be able to bring in spec alpha, and we should be able to bring in the generators. So what's interesting about Clojure spec is that we can define a kind of criteria, or say, well, this is a number between X and Y, or this is a string of this length. Well, actually, we can use any predicate for that, and then we can generate using them. So what we can do is we'll go sgen, and then whatever you want. So like the predicate we're going to use is it a string? So that's the predicate it needs to pass, and we can generate a generator then. So that's our generator. So we've generated a function that will generate a string, and now we can get a sample of that. So let's get a sample, and I don't know, should we have 10 strings? But of course we can do lots, and we've got a load of strings here. So now what we're going to do is do some generative testing on our prefix function. So it's prefix upper bound. So we're going to run prefix upper bound on a sample of strings and see what we get. This type of kind of testing is really, sorry I haven't imported that, so we'll bring that in, and then we'll bring this in, and right, we've got a null pointer exception. So so that's interesting, and of course what you saw when I generated my strings is that I've got some interesting strings here, but I've also got null. And so my generative testing has shown that so what if I do that? We've got a problem. What happens if I do an empty string? We've got a problem as well. So what we need to do is simply guard against that. So we can say when s, then we'll bring that in. Now that will solve one problem. We'll bring that in. So is that going to work now? No, because it still has the empty string. So what we'll do instead is we'll use when string is blank. So what we'll have here is when not. So when the string is not blank, we're going to run if it's empty. Sorry. That's me being stupid. There we are. So when the string is not blank, then right. So what we need to do is just pop up and import closure string str, so we can load that namespace again, and so we can. There we are, and then do that, and suddenly we have a system that works. But we can do that for 1,000 now, and it works. So that's super now, and in fact we can just, if you want, you can eyeball this. So we can just kind of play around with this, where we can put a vector of the original and then the result of it, and we'll map across that, and suddenly you'll see, well look, we've got S to T, we've got IIM to IIN, it's nil to nil, B0 to B1, it's all working well. So we've built this nice little function, which I will put up, and we'll include now in our proper namespace. So we can do that above the comment block. So that's a nicely written and tested thing that will work with different strings and give an upper bound. So we can now use that. So we'll go back to our original problem, which is here, and now we can say replace this with prefix upper bound G70. What we should do, that's where we restarted the REPL, so we'll just get a store back. We'll get the set for map targets, and then we'll do that. And look at that, we've got G70.9, and just to be really clear, we're getting the same result using our new bounds. So what that means now is that I can start thinking about how we build this properly. So given an input and string, we can generate the upper bound, and then we can use those two to get a sequence of ref sets, ref set identifiers that match that prefix. So let's do that now. So we'll just write some code. So say we're passed in this string. So we'll do def s is G70 just to start with. Let's call it prefix actually, just it'll help our naming. So that's our prefix. So we're going to say so let just kind of allows us to set symbols to values. So why don't we say the index that we've got is this thing here. So that's our like index of stuff. But at the moment it's everything. It's everything in SNOMED CT, all of the reverse, all of the maps really. So we don't want that. That's too much. But that's fine because we're not. It's a reference to it. So unless we start using the data, it's not going to pull all that data in. It's not going to be quick. So the lowest point is simply going to be the ceiling, isn't it? So so we'll take this. And we'll say the least is the ceiling of our index, and so we better say def ref set ID, and we'll just say we've got it for testing here, so we'll put that in there, sorry, and then we've defined our prefix here, and then we can put ref set ID here, and we can put our prefix here. That's returning nothing, that's fine, so but it's, that's all right. So that's the least point. And of course the greatest point is going to be the floor, isn't it, that we calculated before. And so we'll do a to array. I mean, this is really very straightforward. And we'll take the prefix and we'll say the prefix upper bound of our original prefix. And actually, why don't we... just for debugging purposes, so our greatest is that, and our least is that. So we know we're on the right track here. So we've got least and greatest. And I suppose let's just, what happens if we put nil in here? Because that might be an issue for us. So if we define that as nil, what happens? Oh, that's a bit weird. And in fact, it's in the wrong reference set, so that doesn't seem right at all. What happens if we use an empty string? I don't want you to do that. Okay, that's better. So we get an empty string in the reference set. So that's kind of what we expected, I suppose. And what do we get when we... so this is kind of exploratory here. Look at that. So we've got the final end. So the first ICD-10 code is nothing, and the last is Z99.8, and that's the ref ID that we know from before. So I think we need to do some validation here, because those didn't seem right when it was empty. And of course these could return nil as well, and so we should just do a check here. So we should probably just define an invalid. If it's invalid if we've got a blank string, because we can just shortcut them, because I don't think that we want to allow this function to return the whole ref set. That would be a different job. We probably would want to stream that live using some kind of asynchronous channel rather than, and then be able to stream it out to our clients rather than bringing it all into memory. So we don't want to do that. So we're going to screen out that. And then we need both least and greatest to be non-nil, so we can just do that. That checks that. So it sends an and, it's least and greatest, and truthy values are non-nil, so we know that's going to work. And we can use the navigable set's own comparison to compare the least and greatest, because we want to make sure that least and greatest are either equal or the right way round. There'll be some edge cases where you have empty strings where the greatest is less than the least, and that's not what we want. So What we can do here is, so what we should have now is to be able to run this. Yeah, that's the answer I wanted. Is we're getting the results from something else. So here we've defined the prefix, and we're just getting our objects. Now, if you remember, we can just go map sequence just to debug this. And we've got all the G72s, which is what we'd have expected. And if we change it to G73, then we get all the G73s. So that is working as we want. So what we need to do now is take this data and extract the upper and lower significant bits of the UUIDs. And that's going to be really easy. So, and then we make a UUID and then we fetch the RefSet ID for that. So we can do, we can do this in line, but just to show how easy this is, if we define our fake data, so we'll define X as this, it's just data. It's a list, and so there we have X. So I can show you what X is. It's the same data as we had before. So if we can use something called destructuring here, so we can say RefSet item, RefSet ID rather. We can use the code. We can say the most significant bit, and we can say the least significant bit of X, and we can just to show that it's working. Let's do reduce a map with the most significant bit is MSB, and the least significant bit is LSB, and we're just going to throw away the rest. So what this should do is return a map of MSB and LSB. It works. So can we do, instead of using that, we can actually just create a UUID with the most significant bit and the lowest significant bit. Ta-da! We have that. And actually then, once we have that, we can so we'll say the UUID is that, and then we can use our service. We can use our service now, so we'll say get RefSet item, and we'll pass in our store and our UUID and see what we get. And it works. So we have G73, because that's what we were asking for, G73.6, and we've got reference component, and there's our RefSet item. So we need to do that for all of them. Well, when we're doing this kind of work, we're just chaining data. We're just getting data flowing. So we can use a flowing macro actually. So what this does is it passes the result of the subset, which, if you remember, was just that funny list of objects. So what we're going to need to do is first of all map it and turn it into a sequence. Should we just test that that's going to work? Yeah, so that works. And now what we want to do is return the UUID, so we can just use that code that we had before, which we'll copy from here actually, and stick that in. And actually we don't need the let bit there, do we? So we'll pass this in here. So we'll map it across a function which says let RefSet and that's what gets passed in. So MSB and LSB will suddenly have our answer, and we simply ask for a UUID. So what we should have now is a list of UUIDs for each, and then what we can do is we can map that as it comes down the line, and we can say please fetch the RefSet item using our store using that UUID. And what you'll find then is we have all our answers. Now we could carry on. We could say, well, okay, just give me all of the referenced component IDs, and it will just give us the answers, and then we could put that into a set. Well, we could do that, but actually we've just thrown away a load of data, so I don't actually see much point in doing that. And in fact, what I might do is leave this as the function, so that we get our item, generate the UUID, return the ref set item directly from the thing. So that works. So what we need to do now is turn this into a function. So I already have one called getReverseMap. We could call this getReverseMap prefix or getReverseMap range. I think we'll call it range. And what we'll do here is we'll define the arguments as the store, which is fine, and then the ref set ID, so we'll get the client to pass that in, and then the prefix. And what you'll find then is we put that in here like that, and that should be working. So now we should be able to go get reverse map range from our store with whatever that ref set was, so ICD-10, and then let's use G73, and what we should have here is all the G73s, and indeed we do. Just for the avoidance of doubt, let's just check. Oh my goodness, it works. So we've got all the A1s, so we've got our prefix match working. But I suppose if you look, we're calculating this prefix, so I suppose what we can do is Clojure allows us to define our functions with different parameters. So what we might have here actually is we'll use this as the lower bound, and we'll use this, and we'll allow the user, if they are really expert, to pass in 4 parameters, the third being lower bound and the fourth being upper bound. But if upper bound is nil, then we're going to calculate it for you. So what we'll do here is we'll, for this one, what have I done here? That's not right. What I'll do here is call ourselves get reverse map range with a store ref set ID prefix nil. And what that will do is, if you just pass in 3 parameters, it'll basically call itself with lower bound being the prefix and upper bound being nil. And then all we need to do here is, so this one needs to be lower bound. And then the floor needs to either be the prefix. So if we've got an upper bound, if upper bound, please use it. If not, we'll generate it for you. And so that works. So that's really easy logic, and that will get the upper bound for us. Calculate the least, the greatest, whether it's invalid or not, and then if not, it will give us all the ref set IDs. And I think that will work. So we can just test that for ourselves now. So we can do that. Let's put in A12 just to, okay, that's not very helpful. A19. But if I say the upper bound is B20, okay, we've got all the A's and all the B's. So that's kind of it really. We've got our reverse map range. So I can put that nicely up here, and then just to finish off, then we better deal with this. So as some of this is performance sensitive code, we'll be wanting to just give a hint to the compiler, so it doesn't need to use reflection. So this is a navigable set, we know that. Oh gosh, look, and so this needs to be lower bound as well. So check that works. Yeah, it does. crumbs, that's quite a large amount of data. So that's good. So I think that's pretty much it for that. So now we have Hermes with an ability to, what I'm going to do is move it closer to get ReverseMap. We'll stick these two functions here. So there's some, and then what we need is a doc string here. So what we'll say is this returns the reverse mapping from the reference set specified, performing what is essentially a prefix search using the parameters. So parameters are store is our store, so a map db store, because that's our, this is our in detail thing. So in fact we should probably we will do that because that will help. In general enclosure, you don't need to do that actually. In fact, you're better looking at and only doing it for when your linter tells you that you've got reflection. And in fact, there's a parameter we can set warn on reflection, which is here. Which when it's compiled, it will give a warning that it's using reflection to deal with something. And actually, we don't want that for this, because this is performant, needs to be performant code. So the reference set is the reference set in which to search, and then we'll say the lower bound. It's nice to get these all lined up. Is the lower bound prefix, and that's inclusive, and then the upper bound is the upper bound prefix, and it's exclusive, so it won't include whatever you type in there, or we'll calculate it. So let's do it prefix, and that's prefix lower and upper bounds determined